All right, so the second part of section 3.2 is solving systems by elimination or addition. So this is another algebraic method of solving systems, similar to substitution, where we don't have to use a graph to find the ordered pair where the lines would intersect. So again, I've got a whole bunch of words to explain how we solve a system by elimination, but if you would rather just see the process and kind of get a feel for it from that, that's fine as well. So the first thing you want to do is get the equations so that they look the same. It's easiest if both the variables are on one side and the number, the constant, what it's equal to, is on the other. And then our goal is to add the equations together and get one of the variables to eliminate. Now thinking about what kind of numbers eliminate when we add, and they are opposites. So we may have to multiply one or both of the equations by a constant so that the coefficients are opposites and they'll cancel. Once we add the equations together, one of the variables cancels. We'll have one equation with one variable that we can solve for, and we'll substitute that value back into one of the original equations to solve for the variable we eliminated. And of course, we will write our answer as an ordered pair. So let's see how this process works. Looking at my first example, the first equation has x and y on opposite sides of the equal sign. So what we really want to do is rewrite that so that it looks like the second equation, where the variables are on one side and your constants on the other. So I'm going to go ahead and subtract 4y from both sides and subtract 12 at the same time. My second equation is already organized nicely. And now I'm going to take a look at which variable might be easiest to eliminate. A couple of things to already have opposite signs, so you will be multiplying by a positive, which is easier to work with than multiplying by a negative. But looking at the x's, they have smaller numbers. So that might be easier. Noticing we have a 63 in our second equation, I might not want to multiply that by 4. So I'm going to eliminate my x's for that reason. And in order to eliminate my x's, I have to find a number that 2 and 3 both go into, the least common multiple. Kind of similar to finding a common denominator when you're adding and subtracting fractions. Well, the least common multiple of 2 and 3 is 6, but I need one to be positive and one to be negative. So I'm going to multiply my first equation by a negative 3 and my second equation by a 2. Now when we do that, we have to multiply everything in the equation by those constants, because whatever you do to one side, in order to keep it equal, you have to do to the other. So let's see what happens when I distribute my negative 3. I get a positive 6x plus 12y equals 36. Distributing my 2 in the bottom equation, I get a negative 6x plus 6y equals 126. So looking at my x's, they now have opposite coefficients. So I'm going to add my equations together. X variables cancel. 12 plus 6 gives me 18y equals 162. Dividing both sides by 18, I get y equals 9. So I'm going to substitute that back into one of the original equations, and I think I'm going to choose the first one because it has smaller numbers. So replacing the y with 9, I get 12 minus 2x equals 36, subtracting 12 from both sides, and dividing by negative 2, and of course writing our solution as an ordered pair x, y. So my solution is negative 12, 9. All right, let's look at one more. This one is already organized nicely. I don't have any opposites, so I'm probably going to eliminate the x again because it's got smaller numbers. Least common multiple for 4 and 3 is 12. So I'm going to multiply this by a negative 3, and this one by a positive 4, so that again, the coefficients are opposites, so I can add them together and get them to cancel. Distributing in my first equation and my second equation, adding my two equations together, negative 12x plus 12x cancels, 15y minus 16y is negative y, negative 21 plus 24 is 3, dividing by a negative 1, I solve for y. And then I can choose either of my original equations to substitute that back into. You could substitute it into either of your multiplied equations, but those have bigger numbers, so it's going to be easier to look at one of your original ones. I'm just going to go ahead and use this one. It's got smaller numbers. So we got 3x minus 4 times negative 3 equals 6. 3x plus 12, subtracting 12 from both sides, and dividing by 3. So we got our negative 2, negative